Okay, calculus, let's pick up where we left off. Number 3. It says, this is where it wants dw ds, the derivative of w with respect to s, and the derivative of w with respect to t. So as a reminder, dw ds would be dw dx ds plus dw dy ds. So we'll do that first. What's the derivative of w with respect to x? It should be 2y. Derivative of x with respect to s should be 2s. Derivative of w with respect to y is 2x. Derivative of y with respect to s should just be 1 over t. So this should be 4ys plus 2x over t. Now, y is s over t, so this should be 4s squared over t. X is s squared plus t squared plus 2s squared plus 2t squared over t. So that should be in total 6s squared plus 2t squared all over t. If you want to reduce it to its component parts, you could say this is 6s squared over t plus 2t. Either one of those is fine. Now let's do dw dt. It's the same thing, just replace the s's with t's. So we already know it's 2y. Now it's times 2t plus 2x. So the derivative of this thing with respect to t would be negative s over t squared, because it's t to the negative first power. So that's 4yt minus 2x over t squared. And we sub. Y is s over t times t, so it should just be 4s. X is s squared plus t squared, so minus 2s squared minus 2t squared. Both of these are over t squared. Now, I forgot the s. Times s, somehow I left it off. So this is actually s cubed, and this is t squared s. So this is 4s minus 2s cubed over t squared. This should just be minus 2s. So in total, we should have 2s minus 2s cubed over t squared. And that is our derivative of w with respect to t. Now one last thing on the next page. Sometimes we have implicit partial differentiation. So for dw dx, it's the derivative of f with respect to x times dx over dx plus the derivative of partial of y times dy dx. What happens here is, well, dx divided by dx should just be 1, the derivative of x with respect to x. So it allows us to move the partial derivative to the other side by subtracting, and then divide by the y partial derivative, so you end up with negative partial derivative of x over partial derivative of y. The only requirement is that obviously you can't divide by 0, so we know that the partial derivative of y can't be 0 for this to work. And there's more equations. You can do the same thing with dz dx and dz dy in the event that there are 3 equations. So for a, we'll find dy dx. So the first things I need to do are find the partial derivative of x. So we've got a constant with respect to x, and so this is just negative 2x. Partial derivative with respect to y is 3y squared plus 2y minus 5, and then 2 constants. Now it says all I have to do is take the partial of x divided by the partial of y and flip the sign. So negative 2x over 3y squared plus 2y minus 5 becomes actually positive 2x over 3y squared plus 2y minus 5. And that's it for the partial. So we can do b as well. Now it wants both the partial with respect to of z with respect to x and y, so I need to find all three partials. So fx is going to be 6xz minus, this is a constant with respect to x, 2xy squared, constant, fy, constant, negative 2x squared y plus 3z, and fz is 3x squared plus 6z squared, constant, plus 3y. Now same rules to find the dz dx. I take the partial of x divided by z, so that'd be 6xz minus 2xy squared over 3x squared plus 6z squared plus 3y, and I take it and flip the sign. So that would be instead 2xy squared minus 6xz, so it just reverses our subtraction in the numerator, over 3x squared plus 6z squared plus 3y. Do the same thing for dz dy. Normally it's the negative of negative 2x squared y plus 3z over 3x squared plus 6z squared plus 3y, which we'll just flip the signs. So we have 2x squared y minus 3z over 3x squared plus 6z squared plus 3y. And that is all for 13.5.